Hello and welcome to the presentation about our valve sizing program called ARI myValve that you find on our homepage under the account of myARI. So I would like to do the sizing today about two products, an ARI control valve and called ARI Stevi, and an ARI safety valve called ARI Safe for a pressure reducing station. And I would like to show you the example that for the sizing that we are going to do now. You see here the pressure reducing stations, and we are going to do the sizing of this control valve and in addition about the safety valve. So, and therefore we have to start the ARI myValve on our homepage that you find under the account of myARI. So I open myARI and you see here by myARI you see on top the button myValve. So now we open myValve and here you've got an overview about the products that you can size right now with or here under this account. In the upcoming future, we will implement more of our products so that this myValve tool here fulfill more or less everything that you can do with the full version of ARI myValve that hopefully you have already installed on your computer system. So here you see you can do the sizing of control valves. Self-operated regulators means controllers without auxiliary energy. So you see pressure reducing valves, Predu, excess pressure regulators, our ARI Predex, and the temperature controller, Temtrol. Stop valves, not only stop valves, means isolation valves. You can do the sizing of the check valves as well. Underneath you find our butterfly valves, Z-Trix, the metal-to-metal triple offset design of our butterfly valve, and the VDOX calculation means the double eccentric butterfly valve. You can do a proper sizing of this by the myValve tool here as well. And safety valves and at least steam traps. So for our example about the pressure reducing station, we are going to start the calculation of the control valve. So I open the calculation chart for the control valves. You see, first here on the modules you can change the different type of valves you want to design or you want to size by the myValve tool. So we are going to do this for the control valves, and here on top you see we are on the chart for the control valves Stevi calculation. So then you see show all fields means that we improve here or we add or we open some more fields, some more windows that are useful for the sizing to get a brighter overview, a better overview about the specific data of the valve. So under calculation target, when we open calculation target, we can do the KV calculation for differential pressure or the volume of flow calculation. And what we are going to do is, for sure, first we have to do the KV calculation, and then afterwards, for the proper sizing of the safety valves, then we start the volume of flow calculation, and to do afterwards a proper sizing of the safety valves. But first now, we're going to start the KV calculation. So, conditioned, yes, we've got saturated steam. You can go with liquids, superheated steam, or certain vapor or gases as well. But we've got, in our example, we go with saturated steam. So, as an example, I used an inlet pressure about 3.5 bar. 3.5 bar on the inlet side, and the outlet pressure should be 2 bar. You can change the units here to millibar, kilopascal, atmospheric pressure, and megapascal, and yeah, different other pressure units as well, and PSI as a G pressure is available as well. But we go with bar G pressure. So bar G, 3.5, 2 bar G. Mass flow, you have 3 varieties about the volume of flow, or mass flow. Means we use mass flow, volume of flow, or the heat capacity is possible as well. We go, because we usually get as an information, we get the information about the mass flow for saturated steam conditions. So I choose as an example 150 kg per hour. Under function, you can switch between control valve. This means it is a straight through control valve. We can go with 3-port valves. So you can do the sizing of a 3-port mixing valve or a diverter as well. You can do it both. Or you can do the sizing of an automated isolation valve as well. But in our case, we want to size the control valve. Characteristic, flow characteristic, we have the chance to go with the equal percentage or with the linear flow characteristic, but you know better than me that usually for the steam applications we go with an equal percentage flow characteristic. So we go with equal percentage. Nominal pressure, yeah, we can lift it up to pressure class PN 25, 40, or according to the ANSI dominated markets, we can use the ANSI class 150 or 300 as a flange connection as well. In our case, PN 16 is good enough because we're talking about an inlet pressure of 3.5 bar. So pressure class PN 16 would be good enough. So then we go with pressure class PN 16, and the safety factor. The safety factor means that, according to the flow characteristic and the stroke of the valve, means that we do not size the valve up to a stroke higher than, let's say, about 92-93%, because at the last level of the flow characteristic, there is no proper control possible anymore, and this is and the safety factor doesn't allow a sizing up to 99% stroke. We can delete the safety factor and do a sizing without safety factor by drop down the safety factor to 1.0, but at least for the first time that you do a sizing of a control valve, you should leave it as it is and go with the safety factor of 1.25. Yeah, so now we filled every window, and now we can see how many results we get. So calculation start, and you see product data calculated 2080. That's enormous. So this is enormous, and at least right now this is not very helpful at the moment, because now you do not know exactly what will be the right valve. So now we can filter and build up a deviation list here. So means we can say about the material, or we can choose the material. We can say, okay, we do not need, or we don't want to go with gray cast iron, ENJL 1040, because it's steam. It's just only 3.5 bar, but we recommend that you should go minimum with nodular iron. And cast steel, we can go with cast steel or stainless as well, but for our example, nodular iron should be good enough. So, and then you see we drop it down to 732 options. So now connections, we have only flange connections, so then we leave it as it is. And sealing, yeah, we can do a drop down of the ceilings by using just one sealing or stem sealing or packing. Sometimes you call it packing, sometimes you call it sealing, depends. For saturated steam up to a temperature of 220 degrees C, we recommend the PTFE V-ring unit. So therefore I would go with the PTFE V-ring unit. So, and you see now just available 138, much better. Plug variation, yeah, show all. And you see a high variety of plug variations. So you find the parabolic plug, which is our standard plug design for control valves. So you can have a stellited parabolic plug with soft seat, a perforated plug, or a pressure balanced parabolic plug. In this case belongs to experience and belongs to a rule of thumb. So as long the delta P is lower than P1 divided by 2, so in this case you can or you should go with a parabolic plug at first. And in our example we have exactly these conditions, so therefore I would go with a parabolic plug. But for sure, if the differential pressure is much higher than P1 divided by 2, then you should go with a perforated plug, or with a seat guided plug. That could be a perforated plug, or it could be a V-port plug design. But for our example, we go with a parabolic plug. So chosen result is just 37. So now I would say for sure we can do a higher grade of deviation, means we can say, okay, we can drop it down just to 1 kVs value, but to have an overview about the possible kVs values, I would leave it as it is at the moment, and the same we should do with the nominal diameters as well. So most of the time, first you use the smallest diameter, and this is for these conditions is a diameter 15 with kVs 4. So we mark it, and then you see as a result, you see that you find a stroke about 93.5%. So it's still in under a good flow conditions, or flow conditions. 93% of strokes, sorry for this, and we could use kVs 4. But if you know that the mass flow could rise up from time to time, so then we can go with a kVs value that is one step higher. So then we go back to the calculation chart, and then we can choose the diameter 20 with a kVs of 6.3. 6.3 belongs to diameter 20. So and then we see, okay, stroke is about, what is written here, about 82%. 82% stroke. Sounds a bit better than 93% of stroke. So I would say the kVs value of 6.3 is exactly the requested kVs value that we should use for these operating data. So we go back to, or what else can we do here? So you see, by the kVs of 6.3, we have an outlet speed about 82 meter per second. That is really nice result, and it's lower than 100 meter per second, so that's very easy to handle it by the valve. And the sound pressure level is much lower than 85 dBA. 85 is the border that we should not override. And insulation, we can use a valve without insulation, or we can do the sound pressure level calculation by a thermal or acoustical insulation. To be honest, I have never seen an acoustical insulation outside in the field, so usually you go with a thermal insulation in the field. So when we press thermal insulation, you see that the sound pressure level drops down to 73 dBA. And here, by these eye here, you get some more information what is behind the calculation of a thermal insulation. Means that for the calculation, we use a thickness of the insulation just about 60 mil, and in real life you find, usually for saturated steam, you find an insulation about 100 mil thickness. But nevertheless, this is just 60 mil insulation, and it drops down the dBA value. And the beauty is that we can do the line sizing here. So means by the P1 pressure and diameter 20 that belongs to the selected valve, we have a velocity in the pipeline about 44 meters per second. This is much too high for saturated steam. It should be roughly between 20 and 30 meters per second. So then we increase the line to 25, and you see that's perfect. That's exactly between 20 and 30 meters per second, means it's about 27 meters per second. So then we automatically size the inlet pipeline. And we can do the same for the P2 pressure, means for the outlet line. So then we increase it to diameter 32. 32 is exactly perfect diameter for these conditions. So then we have a velocity that is around 24 meters per second. That's fine. So we do the sizing of the control valve, and in addition we can do the sizing of the pipe diameter for inlet and outlet as well. That's perfect. And now here we've got 25 and 32. We sized the valve for diameter 20 right now, and it wouldn't be wrong to go with diameter 20, fair enough. In this case, I would go back to the calculation and would go, or will search for a valve in diameter 25 as well, because the price difference between diameter 20 and 25 is very, very low. And it makes sense to build up the system without a reducer that makes it much easier to build up the complete pressure reducing stations. And therefore we can go with diameter 25 and the requested or the calculated kV value of 6.3. You see, diameter 25, 6.3. And we go with, we can do another filter. I forgot to do another filter. Oh, sorry guys, here, by the type. We can say show all, and here you see the different designs of our valve. So means it's our design 470, 440, means the Pro design, the Smart design, and the Vario design. So, and now you have to know exactly what is behind these different designs. We love to go with our Vario design as long as it is suitable. Here you see the 448 is suitable. In this case, I would recommend to go with a 448. And when we press 448, so then we have just a selection of 11 different kind of valves. And then you see here only 448 is mentioned here on the board. And as I said before, diameter 25 with our KVS 6.3. This should be the right valve. So again, we have 82% of stroke of the valve. Here is the definition of the valve. And line sizing, yeah, we set diameter 25 on inlet, outlet should be 32, about 24 meters per second. That's fine. That's perfect. And when we compare this to our drawing, then you see exactly here we've got an inlet of 25, isolation valve and the control valve, same diameter, means diameter 25, and then we have a reducer, and then it goes up to diameter 32. So this fits exactly to the drawing, and this is how we build up the system in the past. So now back to the sizing. So now we sized the valve. It is 22448. This is our article number or article code. It's PN16, diameter 25, equal percentage flow characteristic, and the KVS value of 6.3. Stem sealing, PTFE ring unit, parabolic plug. Perfect. So the beauty now is that we can do the sizing of the actuator as well. So we press actuator, and then we can choose between an electric or a pneumatic actuator. Yeah, for pressure reducing stations for saturated steam, for sure, usually you go with a pneumatic actuator. We select pneumatic actuator, extended stem. That's what we choose. And now we can select the actuator. And here you see, you see the DP30 is big enough for this small diameter 25 with KVS 6.3. So we go with a DP30. Closing pressure should be minimum 3.5 bar. This is our inlet pressure, but the actuator, the fourth of the actuator is strong enough to fulfill a closing pressure about 16 bar. So the actuator is strong enough for this execution. So, and then we choose this actuator, and here you see the beauty is you can get the data sheet. You find the data sheet about the actuator here, the operating instruction, and the 3D step or DWG files are available as well. Yeah, and here's the description of the actuator. So, beauty now is that we can save the collection. We have to press here this mark here, save calculation. So now we can say project number 123, and description should be test. We can write in test, whatever. We can fill in a tag number as well, 456, and we can say a node, it's control PRV, for example, just as an example. And then just press save. Done. So now we saved it, and we did the sizing of the control valve. That's done. Now we can go back to calculation, and we have to do for the sizing of the safety valve. That's what we are going to do in the next step. We need the Qmax conditions of the control valve. So therefore, our calculation target has to be changed to volume of flow. And now we fulfill the volume of flow calculation for our selected valve. So we have an inlet pressure, 3.5 bar for sure, and our outlet pressure was 2 bar. But the set pressure of the safety valve is higher than 2 bar. So in this case, we select 3 bar as the set pressure of the outlet, set pressure of the safety valve. So and therefore we do the Qmax calculation for the inlet pressure of 3.5 to outlet pressure of 3 bar. And we selected the kV value of 6.3, so we have to fill in 6.3 and diameter 25. And that's all. That's all. No other fields has to be filled out, and then we press calculate. And as a result, you see the Q max, the maximum flow, is about 205 kg per hour. And now we know we have to do the sizing of the safety valve according to 205 kg per hour as a mass flow and a set pressure about 3 bar. So now we change from the calculation target for control valve, we change to safety valve, and we go, in this case, we go with DIN EN calculation for safety valve. You see, you can do the calculation for a semi-nozzle ASME confirmed safety valve as well. In this case, for our example, we go with a safe DIN EN calculation. So, program starts. Yeah, we have condition is saturated steam. Set pressure, 3 bar. Back pressure, usually it's 0. You can fill in certain back pressure if there is a back pressure situation, but usually there is no back pressure situation if you assemble a pressure reducing station somewhere in an industrial, for an industrial application. Mass flow, 205 kg per hour. You see, we can change the units here, but we go with kg per hour and bar as a unit for the pressure. So pressure rise is 10%. You can change the pressure rise, but usually and according to the regulations, you should leave it as it is, because by the regulation it is written that the pressure rise is about 10%, and therefore the 10% are fixed already here. You can change it, but usually you leave it as it is. So we leave it at 10% pressure rise, and then we press view results, and you see 1,339 calculated valves could be used for these conditions. But we do a deviation. Designation, so we do not go with the ANSI, semi-nozzle ANSI valves, we do not go with Safe P design of our safety valves, and we don't want to use the thread connection. We want to use our safe means our safe design for this saturated steam pressure reducing station. So we go with safe. Material, gray cast iron. As I said before, we do not recommend gray cast iron for saturated steam conditions, so we can go with carbon steel, stainless steel, or nodular iron, and we usually use the nodular iron for saturated steam. In this case we go with nodular iron, but you can go with carbon steel as well. We go with nodular iron, so we drop it down to 239, and yeah, and we have the deviation about the designation and the material. We can drop down the nominal diameter and the pressure as well, but and the connection, but I think here we just find flange connection, yeah. And usually you go with the lowest diameter of the safety valves. You can lift it up, but the lowest diameter means the valve that is on top here. This is, in most of the time, this is the right design. But regarding design, we should do a deviation about the design. Show all, and yeah, now. Usually you use the smallest diameter of the safety valves, and therefore the lowest diameter or the smallest diameter is all the time on top here. So therefore we go with diameter 20 as an inlet and 32 as an outlet. So, and here you find all the product data. It's a full lift safety valves. This is our article number. And oh yeah, here this is a closed bonnet design. Usually we go with the open bonnet design, but this is something you can change by, or you have the chance to do a deviation by the design in this myValve tool as well. So usually we go with the open bonnet design for saturated steam, but the closed bonnet design is sometimes a better solution, because if this pressure reducing stations is close to human beings, so then it protects the human beings by an operation. So when the safety valve opens, then steam can come out by this open bonnet design, and therefore sometimes it's much better to go with the closed bonnet design. On a steam boiler, we would recommend the open bonnet design, because this is on top of a steam boiler, and usually nobody is next to the safety valve in case of an operation of the safety valve. But here it's not wrong to go with the closed bonnet design. Yeah, we can do some further deviations by going here to the right, and then you see for plug. For the plug variations, so we can use you find different kind of plug variations, like the EPDM plug, the SHR plug, or the metal-to-metal sealing plug design. For steam, we recommend the SHR, steam and hot water resistant plug design, up to a temperature of 220 degrees C. So therefore we select the SHR plug right now. And bellows, yeah, this is for saturated steam. We can use the bellows as a sealing or as a back pressure comprehensive bellow, and therefore we have to know exactly the length and the amount of elbows of the outlet line of the system or in the plant. This is what we do not know so far, and therefore we go without the stainless steel back pressure comprehensive bellow. So, and now we can select our valve. So this is usually the one that is on top, because this is the smallest size, the lowest diameter, and this is diameter 20, inlet 32 on the outlet. So we select the valve, and now here you see it is our article number 25901, and then the diameter, full lift design, nodular iron pin 40 flange, diameter 20 to 32. This is a description about the valve, SHR plug, 3 bar set pressure, and so on. So, and yeah, now we can save. We can do the saving of this selection as well. So then we say it's same project, it's test number 1, and the tag number is not 456, it's 789 as an example, and then we can save it. So now we saved it. And yeah, back to our pressure reducing station. So we did the sizing of the pressure reducing station, means of the control valve, diameter 25, kVA 6.3, and the safety valve in diameter 20, inlet to 32 on the outlet, SHR plug, set pressure 3 bar. And we did the sizing of the inlet line, diameter 25, and the outlet line, diameter 32. Well done. So, and when we go back to the myValve sizing tool, then we can open our saved sizings by this button, load calculation, select the calculation, and now here on my computer under downloads, you find here, you see 789 for the safety valve, 546 for the control valve. You see the calculation, and we can reopen the calculation now. Open, upload the file. Here we go. And here is again the selection, tag number 456, control PRV. This was our node, and you see 3.5 to 2 bar, and this was the selected valve, means diameter 25 with a KVS value of 6.3. Regarding the storage, or where you storage or save the calculations on your computer, this depends to the equipment of your computer. Here on our computers, on my computers, it's under downloads. Thanks to our myValve tool, we did the sizing of our pressure reducing station today. Thanks for listening, and if you need further information or you've got further questions, then please do not hesitate to contact us now in the chat, or later on by an email or by a telephone call. Okay, thank you so much. Bye bye.